Hi, my name is Lars Aurdal. I'm currently head of research at an Oslo-based startup, Findable.ai, specializing in building document understanding, so for the building industry. And welcome to my channel, ImageFu. You have to have a name. And my focus in this channel will be on all things image processing, but with a special focus on more traditional image processing techniques, so not necessarily neural network based, but that still have kept their relevance in this very neural network based new reality. I've been in the field of image processing for more than 30 years. I did my master's back in 91 in electronics and signal processing at the Norwegian Polytechnic. And then I started my PhD work in 93 in Paris at the ENST in medical image processing. And I defended my thesis in 97. And ever since, I've been in the field of image processing, both in private and government positions. I've taught image processing at the Norwegian Polytechnic, also at the University of Oslo. So I think I have a good grasp of the development in this field in the last 30 years at least. And as I said, what I want to remind people of, and will be partly the focus of this channel, is that a lot of the more traditional image processing techniques still maintain relevance, even though neural networks obviously have had an enormous impact in this engineering field. The first video that we're looking at today, in this video, I want to answer a question I've been getting a few times lately. What is meant by saying that a neural network is convolutional? So what is a convolutional neural network? And to explain that, I want to take one step back and actually answer the question, what are convolutions in traditional image processing? So today's first video, I'll show you a very simple example of convolutions in traditional image processing. Then my next video, I'll stay in traditional image processing and show you two more specialized convolutions that are used for edge detection. And then in my third video, we'll look into what does this mean in terms of neural networks, and how can this be used to explain what's convolutional about a neural network. I'll try to keep the math at a reasonable level. I do expect that at least some of these installments will require first-year university engineering mathematics, maybe even parts of a second-year curriculum. But I'll try to keep the math down and to explain also in words what I mean by the different mathematical approaches that we'll touch on. So I hope people find this interesting, even though some of the mathematics might be lost on some of my listeners. So with that, I suggest we start looking at convolutions in traditional image processing and understand what is meant by that and how what they actually did in traditional image processing. Hope you found this interesting. Now, I'll be illustrating the different steps in convolutions using Python and using a Jupyter notebook that you see here. This could be done in any programming language, basically, or most of them at least. I don't aim to teach Python. I assume you have a good grasp of Python if you want to use these notebooks that I'll make available in a GitHub repo. I'll link to it in the comments below. But there's nothing very particular about Python and Jupyter notebooks for this. This can be done in a whole range of programming languages. For this particular notebook, we'll be using the NumPy, so the numerical Python library of Python. The rest of the code is basically just for displaying images. I'll use Plotly for that. You'll see why in a moment. and some simple setup just for visual aspect of this notebook. As I said, I won't really be trying to teach Python. I will comment on, in certain instances, on particularities whenever sort of Python contributes something essential to how things are done. But in general, what I want to convey is the underlying image processing and not really anything Pythonic in particular. Although Python is an excellent choice for experimenting with this kind of thing, and Jupyter Notebooks as well. By the way, I'm running this in Cursor, but there's a whole range of editors that you can use that basically have the same type of functionality. So what are convolutions? For almost every practical purpose, you can think of convolutions in images as being the same thing as two-dimensional filtering. I'm showing a lot of math under the carpet here, but as I said, for practical purposes, you can think of it like that. And that sort of leaves the question, what is a two-dimensional filter for use in an image? And that's what I aim to show you in this video. I think the easiest is just to show you what such a filter looks like. So this is just code for calculating the values and displaying it. This is what the filter actually looks like. So it's a very small 3x3 matrix with values set to 1/9, and you understand why the values are 1/9 in just a moment. A very nice thing about image processing is it's so easy to show the effect of different operations. And I'm going to apply my filter to an image of a leaf. Originally a color image, just a leaf. And so a color image, that means typically you have a red, a green, and a blue channel. And in my case, I'm using, for each channel, 256 possible values for each channel. So the red channel, for instance, have values ranging from 0 to 255, etc. Why that choice? It's a typical human visual system can distinguish, I think it's 60 to 70 gray levels. So if you use a much higher number of levels, so 256 in total, and for each channel, the thinking is that if there is a slow gradient in luminosity or color in the image, it should still appear as smooth to a human observer. But to keep things simple, I've decided let's just look at the luminosity part of this image, so the gray level image. Now, every pixel is a single value, values between 0 and 255. This is a gray level image. And imagine that this image had been taken in, for instance, very poor lighting conditions or with a very cheap and simple sensor. Then you wouldn't get this smooth image of a leaf. You'd actually get a very noisy image. Show what I mean by noisy if we zoom in on part of this nerve in the blade or in the leaf. You see that it's very grainy, which is typical of noise. And what I've done is I've just taken my original and I've added in normal distributed noise. There is a little trick to this because I first convert my original leaf image in gray levels to float. Then I add the noise. Then I clip the values to be between 0 and 255. And then I convert it back to unsigned integer 8. Why do I do that? Because when you add in noise with this much, with a variance as high as this, then some of the values might overshoot the limit of 255 or undershoot the lower limit of 0. So you have to make sure that the image stays within the acceptable bounds for an unsigned integer, unsigned 8-bit integer image. That's the only reason for doing this process. Now, we're going to filter this image, and well, I'll show you the function for doing so in just a moment, but let's just switch over to Excalidraw to show you how this is done practically. So look at, here's my, need another tool. Here's my filter, right? And let's say I'm trying to get the filtered value centered on this pixel. So I'd center my filter on that pixel. And what I'm going to do is I'm going to add up all the pixel values underlying the filter. So 30 plus 33 plus 30, etc., up till the last value of 28. And then I'll divide that sum by 9 and round to the nearest integer, and I'll get the value of 30. You can try that if you want. I think it should add up. Why are the filter values 1/9? Because actually what you're doing is you're multiplying as you go each value, 30 by 1/9, 33 by 1/9, etc., and summing up as you go. And that's basically how you do the filtering. So you just, next thing you do is you move it one step ahead, and once you reach the end of the line, you go to the next line, etc. But this kind of begs the question, how do you deal with the situation, or I can show it up here, when the filter sort of sticks outside of the image domain. So how, for instance, do you calculate the value for this upper left corner pixel where actually 5 of the filter coefficients don't really have a corresponding image value? The very standard way of doing this is you add in a border around your image. And this border, you can set it to whatever values you want. Zeros is one possible choice. You can set it to the mean of the image, to 255, or as I have done, which is a very standard thing to do in image processing, you just set each pixel in the border to have the same value as its nearest pixel in the image. And then, if we bring down the filter here, you'll notice that if I center my filter on the upper left corner, now every filter coefficient has a corresponding image value, although, of course, 5 of them will actually be multiplying artificial values, but that's just the way it is. I mean, you will have a border effect, just like you will in the case of 2D or 1D filtering. There is always a border effect before the filter sort of overlays the real data you have. So again, to calculate the value of the upper left corner, you repeat the process. You just add up all the pixel values, divide by 9, round to the closest integer, and you'll have 32. And then you move your filter one step further, repeat to get the new 32, etc. Once you reach the end, you loop back to the first row, first column, one row down, and keep going. Let's go back to cursor. And so I include a function that I wrote in NumPy that actually does this in I shouldn't say Pythonic way. I mean, you could do this in a lot of programming languages. I won't go through every detail of this. It's just a smart way of doing this rapidly, and in the case of NumPy, exploiting the fact that NumPy can do things in a so-called vectorized, so that you can do all operations over a whole image at once, which makes things go much faster, of course. I strongly suggest that you look at this. It's a very typical thing to do in image processing, very useful construct. But for now, let's just focus on the results we're getting. So let's first look at what happens if, as I said, we, instead of replicating the values of the nearest pixel, we actually set the border pixels to all zeros. So if we zoom in on the filtered result, let me see if let me do it again. There we go. You'll notice that there is a dark band in the first column and first row, and particularly dark in the upper left corner. That's exactly what I showed you a moment ago. If you have borders set to 0, then, for instance, for the upper left corner, you're actually averaging in 5 pixels with the value of 0, so that will be very dark, right? And for the top left top row, basically what you're looking at is always averaging in 3 zeros, so darker than the underlying image, etc. Let's look at this with replication padding. In that case, well, you see the entire interest of replication padding, because now you can hardly see, or that there is a border effect, that's for sure. I mean, first row, first column, etc., are definitely influenced by the value of pixels that aren't really in the image, that we have sort of just added in for computational flexibility. But having done this replication trick, you can hardly see the border effect, right? So that's the reason for this replication trick. Let's look at the results of this filtering, so-called low-pass filtering, because you can imagine that if a pixel has a very atypical value compared to the other pixels under the filter mask, then the averaging process will attenuate that. And so it's called a low-pass filter, because high-frequency changes in the image will be attenuated, whereas no change will go through the filter unchanged. We'll look at this in much greater detail. I know this is kind of a hand-wavy explanation of low-pass filtering. I'm making a video on the frequency response of these filters. It's a more technically inaccessible concept, but it's a very interesting way of looking at how filters actually do their thing in images. Get to that in a later video. Let's for now just look at what happens when we apply the filter. So, for instance, let's look at let's pick a part here. You know, here's just the leaf and an edge and the background. The noisy image was, well, very noisy, very spiky, right? And after the application of the filter, you'll notice that this graininess resulting from the noise is all but gone. There is a price to pay, however, if we zoom in, let's say, on this part of a nerve in the leaf. So here is a detail, very sharply defined nerve in the leaf. Here is the noisy version, and here is the version after noise reduction filtering with the 3x3 low-pass filter or averaging filter. Notice that the nerve that was actually sharp and clearly defined in the original, it's less noisy, that's for sure, but it's also slightly blurred. And that's the price you pay for this, using this kind of filter, where yes, it will remove high frequency variations due to noise, but it will equally aggressively attack high frequency noises, information that you would like to have or to keep in the image. So that's the price you pay. There's nothing dictating that your filter has to be 3x3. It could be, for instance, 5x5 or 9x9 or whatever. Keep in mind that if you choose a 5x5 averaging filter, then, well, you have to set the new filter values to 1/25. So now you have 5x5, so 25 filter coefficients. And you need to, since the effect you want to obtain is that you sum all the pixels under the filter, and then you divide that sum by 25, right? And so you obtain the same by just multiplying by 1/25 each pixel and then summing. Now, a bigger filter like this will have better noise suppression. Let's look first at what does zero padding look like in this case. Since this filter will actually be sticking 2 times outside of the image domain, you'll notice that the border effect is now heavily visible in 2 rows and 2 columns. Again, that's just due to our padding with 0 values. If, on the other hand, we do replication padding again, but this time 2 rows, 2 columns, etc., you'll notice that the border effect is visually all but gone. It's definitely still there, as I said a moment ago, but the visual appearance is heavily reduced. If we look at what this does to noise, then let me zoom in on, well, let's zoom in on this part of the nerve in the leaf. You notice that the noise is even more heavily suppressed, but now you're paying an even heavier price for the filtering, because then now this sharp detail in the image, the nerve in the blade, in the leaf, is heavily smeared. So again, this filter certainly attacks high frequency noise, but it also attacks the actual edges in the image that you want to keep. The edges are high frequency content, and they are attenuated or smeared by this very filter. And even more so, since the filter now has a 5x5 and not a 3x3 support. So I'll stop explaining what convolutions or digital filters are for now. My next video, I want to introduce you to two very special filters called the Sobel filters that are used for edge detection, or used to be used for edge detection in images at least. And having explained that, we'll go on to explain how this relates to understanding what's convolutional about a convolutional neural network. Hope you find this interesting. Do download and try the notebook. It should be a simple thing to get running. And see you in the next video.